Today we're going to do another demo. It's very similar to the ones we've done, this one in Python, but instead of using SciPy, we're going to use a different package, PyOptSparse. So let's just do a real quick search for that. So PyOptSparse is not an optimizer of its own, it's a wrapper to many optimizers, one of which we'll use today, which is called IPOPT, developed by another group. So here we go, this is PyOptSparse. First thing you want to do is install it. I'd recommend using Conda here. So just follow this line here to install it on Conda. Once you got installed, well, let me say one of the reasons why you might want to use it is that it wraps all of these different optimizers. SOSQP is the one that's available in SciPy, but that's really the only one for constrained gradient-based problems in SOSQP, and it's a bit limited. So there are some other options here. IPOPT is one we're going to use today. That's a good option. It's also freely available in open source, but it's generally a bit more robust and certainly has a lot more options and output. Later in the semester, you may want to use a genetic algorithm or a particle swarm method. And you can see that once we've got this set up, actually, it's very easy to switch between the optimizers. So it's worth your time to do so. We're going to follow this quick start. More or less, this basically tells you all you need to know to get going, and I'd recommend you look at it. Things do change over time. I'll make a few deviations here and kind of explain things as we go. This is more or less the process. So to start, we need to define a function. Here it's called the objective function, but really it's going to return your objective and all your constraints. So let's start with that. I'll call it the same thing, although you can call it whatever you want. One of the key differences here in PyOptSparse is that it does things in dictionaries. So what comes in is called a dictionary. That's why they wrote xdic, just so you can remember it's a dictionary. Again, this name, you could call it whatever you want. The reason for this we'll see in a second. So let's say, I'll just copy the same line that they have. I'm just going to call mine x. They call it x bars, you call it whatever you want. It doesn't really see, we just have to be consistent. So the reason why you would do this is that you can pass in now different variables by name. So rather than appending all our design variables in one big long array, we could, for example, say, I've got an array of areas and I've got an array of thicknesses, and I can give them different names as input and also different names as I pull them out. So it's just a little easier to pull out the sections of the array I want rather than just making one big array of numbers. For our purposes today, though, it's going to be very simple. We're just going to have one set of variables. I'll just call it areas still. We'll just pretend like it's a structural problem, but it's just, I'll just have the output be called x. So similarly, we need to return our outputs, our objective and constraints in a dictionary form. So we're going to initialize this dictionary of our outputs. Here we got an objective, right? So I'm going to call mine mass. Or sorry, not object, I'm gonna call it mass. And then I gotta have some constraints. I'm going to just use our notation here. I'm gonna use numpy, even though that's not really necessary in this case. And I would initialize my constraints. So I've got two of them. And then I need to put them into a dictionary. And I call it whatever I want. In this case, let's say they were stress. And that's it. So I've got my functions. I also need to return one more thing here. It says this flag called fail, which is going to be true or false. The use of this is that, just to give you an example, in the Bachristochrome problem that we did as one of our homeworks, sometimes you'd get a negative value under the square root. And rather than trying to handle it in some other way, we could just tell the optimizer, we could set fail equals true in that case, not evaluate anything. And it would know, it wouldn't try to evaluate, and it would just be an indication during, say, a line search that I need to backtrack. And we could handle it in other ways, but that can be a convenience where if the function is can't be evaluated at that point, then this is just a way to flag that and tell the optimizer, backtrack from here. So the problem we're going to do is the same one from other videos, just this really simple, basic two-dimensional problem. And I'm just going to copy and paste those values here, so just to save time and so I don't make a mistake. Oh, sorry. All right. So here we go. This is the objective. This is that first constraint. And the second one, trying to copy and paste. There we go. So that's just the simple problem that I've already set up. And that's really it for defining my problem specific things here, or at least the functions. Now I just go through the rest of this to set up my problem. So first I need to define optimization. So I'm going to call this problem. We call optimization, but I need to import that. So optimization comes from PyOptSparse. From PyOptSparse, import optimization. Okay, and I can give it a name. This name doesn't really matter. It'll just show up in the output file. And then I tell it here the function that I want to use. So here I've called it the same thing, but you can call it whatever. Now I set things up in the problem. So first I'm going to do my design variables. I have two design variables. I'm going to give them lower bounds like we normally do. I'll give it upper bounds, positive 5, 5. I'll give it a starting point. Let's say 2, 2, for example. Now I can do this thing where I can add variable group. So I go problem, add variable group. I got to give it the name that I'm going to use here. So this name should match this one, areas. And this 3 is how many I've got. So this is my NX one. This C here means they're continuous variables as opposed to discrete variables, which some of the other algorithms can use. And then lower, upper, and then starting point. So lower, upper, and value is my X0. Okay, so that defines my design variables. Let's now do the constraints. I've got 2 constraints here. I can do lower and upper as well. So this is a little more general than some methods. So we've defined everything already as to be less than or equal to 0, but you don't have to. You could have defined it anyway. And then we just tell it what the lower and upper bounds are. But since we've done it that way, my lower bound is nothing, and my upper bound is 0. Notice that I can do vectors, but I can also do scalars. So if I do a scalar, it's going to set every constraint to be that. Same with design variables. I could have just said my starting point is 2, and it would set that for every value. But I'm just going to keep it as an array here because I may want to change that later. And now I can add constraint group. And I called it stress. I got to match the name here so that it knows functions that are being returned, which one to assign to constraints. Got 2 of them here. The lower is LG, upper is UG here. Okay, and notice the way that this works here. Because I have this function, I can call it again, and I could, for example, add more design variables, and then here I could pull those out too. And again, it's just a convenience so that if I have lots of design variables, I could separate them out. Same with constraints. I could add other constraints. Maybe I've got a deflection constraint, and I calculate that in here. So, oops, it's just a convenient way to separate things out. It's a little more verbose for this simple problem, but can be useful for larger problems. Okay, so I got the constraints. Objective now, that's this one. I just add the objective. I have to do it this way too, because actually some of the officers could handle multiple objectives, and I called mine mass. Okay, so I'm matching that name there. And I think that's it for defining the problem. So now I define the optimizer that I'm going to use. Here in this case, they're using SLSQP. I am going to use IPOPT, and actually, rather than importing IPOPT, I'm going to import this generic name called opt. I'll show you that later in the documentation. That just makes it easier to switch between different optimizers. So I don't have to import each one separately. And then I have to give it the name of the one I'm going to use. So here I'm going to put IPOPT. I could put SLSQP if I wanted to go back and use that one. And this is going to be my optimizer. And finally, I think we're ready to solve. So let's solve and post-process here. So my solution is just follow this. I use the optimizer. I pass it into the optimizer, I pass in the problem, and I have to tell it how we're getting derivatives. In this case, it's called sensitivity. This FD stands for finite difference or forward finite difference. So we'll start with that. Now let's just run this to see if it works. Ran, didn't really print anything. Let's print the solution, see what that does. Okay, so it printed some things out. It's got, you can see the names that I defined are in here, right? My problem, mass gives me a value here, areas. This can be nice too when you've got a lot of things, so I don't have to remember, you know, what is number 14? I can see all these are all areas, these are thicknesses, these are my lower bounds, my optimal values, my stresses and their bounds. Maybe more useful though is the output. So IPOPT produces its own output. I guess it doesn't display the screen here, so it's going to be on a file. So let me just check what directory I'm in here. Okay, I'm just in the space directory here. So in that same directory, I should have a file called IPOPT.out. That's the default. So I can open that up, and this gives me a lot more information. This is just showing what's happening. Let me make this bigger for a little bit. First, it says some of the options. We'll look at that later. It's telling me some statistics about my Jacobian, my number of variables, ones that have bounds, number of inequality constraints. And then here's my iteration history. So here at each major iteration, it's showing my objective, my constraint violations. We'll look at what some of these others mean later. And then it's done, number of iterations. It tells me my final objective, some stuff here, how much time it took, and then an exit message that it found the optimal solution. So that's good. All right, so we'll now modify this so that I can, I'm just gonna put something in here. It's the linter is showing all this stuff because it wants me to put in a doc string, and it's just annoying. Okay, so here we go. Normally you should put in a good doc string, but this is simple, so we're going to do that. All right, let's go back to the documentation. Basically just did the quick start. The guide will have some more info you could look at. So some of these things I've already explained, like design variables, like I can put none to signify that there's no bound on one of them. There's some scaling you can do. Inequality constraint, if I put the lower and upper to be the same, that makes it an equality constraint. It talks about how you can define sparsity and things, which we won't do. Okay, so here's something we're going to do today. We're going to specify derivatives. So we did finite differencing. There are other options you could do. You can do CS for complex step. We're going to define our own. So we have to follow this format. This isn't super clear, so I'm going to try to explain that in a second. Let's point out here on optimization. Notice we can import each optimizer separately, or we can import this function OPT and then just give it by name, and it's not case sensitive, and prefer that because then we can just change this. In fact, let's just do that. If I change to SLSQP and run it, ran, right, and I actually should get a file output for that, which will have less information. SLSQP.out doesn't really say a whole lot, but I have that. It doesn't give me my iteration history, so for IPOPT, it gives me a lot more information and it's more robust in my experience. Okay, so let's go back here. Let's now provide derivatives. To do that, I actually found it more helpful to go to the source here. So let's let me just open up a new window. Go to GitHub here. Let's just go back to the main thing here. In the GitHub repo, there's examples, and you can see some examples, like for example, in the Rosenbrock. Actually, I found this more helpful than what was in the docs currently. So we need to define a new function. They're in a separate function. So let's call this our derivatives. It's going to take in the dictionary, and notice it also is going to return. It's going to take as input. It's going to give me the functions, and they're going to be the same functions I just evaluated here. So that if I want those, I don't have to repeat those calculations. So if I need, say, my mass or stress, right, these objective and constraint values, I can have them already without having to compute them. So I can, for example, just access them directly. I actually don't need them in this case. Let's just compute those derivatives without looking at the format. Let's just do it how we normally would. So gradient of f is going to be vector. First the partials with respect to x0, so that's going to be 2 times x0 minus 0.5. And then the second term is the partial with respect to x1, which is just minus 1. And now let's get the Jacobian of g. That's going to be a that's going to be a matrix, right? So the first one, the first row is going to be the derivatives of g0 with respect to x0 and then with respect to x1. So with respect to x0 is going to be 2 times x0. And then this term minus 4. And now I take the derivatives of this first constraint with respect to x1, that just gives me 1. Okay, now to the next row. This is just in our usual format, usual order. So this is going to be x0, and then a minus 1. And then the last partial is the dg1 dx1, which is this one, 2 times x1. And hopefully I did that correct. Okay, and it doesn't know what x is because I didn't pull it out of the dictionary. And I guess we called that one areas. So there we go. Yeah, okay, now my warnings went away. So that looks fine. It's gonna, again, give me all this annoying stuff unless I pretend I've got a doc string here. Okay, so now how does PyOptSparse want them? Well, it wants a dictionary. So I've got to return this dictionary. Let's call it J. It's going to have this form. So let's see. Objective is mass. I have to tell it what I'm taking derivatives with respect to. So the derivatives of mass with respect to. The reason why it's got this nest dictionary is because, again, I could have multiple variables and multiple constraints. So I could have like derivatives of objective with respect to area, derivatives of objective with respect to thickness. And this also helps with sparsity. If some of them are 0, I don't have to define them. But in this case, let's say I've got mass with respect to areas, and then colon, and that's just going to be df. Yes, I did that right. Okay, and then let's define, I'm just going to move this around. Let's define the derivatives of my stress with respect to areas. This is a little cumbersome, but it helps for generality, is JG. And I think that's it. That's the end of my dictionary. And I just return that. And actually, I think it's the same. I need to return a fail flag. So I'm just going to always set that to be false in this case. And I think that's it for my derivatives. Let's test if it works. So we're going to change our sensitivities here from finite difference. Notice I now pass in the name of the function. So I called mine deriv, or did I call it derivs? Derivs. And I run it, and it ran. And it does say I found an optimal solution, so that looks good. We'll want to check those derivatives in a second, but so far so good. Okay, so unlike SLSQP, IPOPT has options. In fact, it has tons of options, perhaps too many options. So I can set options. Here's some that are set by default. We go to the website for IPOPT, and here's the page about its options. If I scroll through, you see there are just tons and tons of options. Okay, and we won't use very many of them, but we will want to use some. So let's go back to first PyOptSparse and see how to set those. So let's see, probably somewhere under guide or optimizer. I'm just gonna look here. Set option, that'll work. So let's go to optimizer. Optimizer set option. Okay, and there are, and I just give it names and values. So let's say I want to change tolerance. That's maybe what's useful. And I just give it a relative tolerance. The default is 1e⁻⁸. Let's say that's a little bit too tight for me. I'm going to go to 1e⁻�6. So I run that just to verify that that worked. Let's look at my output file, and you can see indeed it tells me all the options that I've set, and it has changed that. So that's great. So that's my convergence tolerance, a relative tolerance. Other ones I might use: maximum number of iterations, maximum wall time. That can be useful for some of them if I, especially some of the gradient-free ones, let's say I just want it to run for some specified amount of time. I can set a threshold for constraint violation, so separate from my optimality tolerance there. The default value here is 1 - 4. I may want to change that. And there are a whole bunch of other tolerances you can look at, but you generally won't change any of these. You can print out more information. The default, so there's 0 to 12. It doesn't really tell me what it means. Just for fun, let's just try and see what happens if I put more. I don't know if these go into the file too. Oh wow, lots of stuff went to the screen. Okay, so that's cool. Lots of stuff. So it's giving me tons of information at every iteration. Probably way more than we want. So let's dial this back and see what that looks like. I do want some information. So 6, yeah, quite a bit. Oh, the default should have been 5. I think, I don't know why it doesn't give anything. That's a little bit, I think PyOptSparse is accepting it with the default for some reason and not putting that all to the file. So if I want to see stuff as I go, it looks like I got to give it at least 6. Yeah. Okay, so it's telling me what's going on. I could see some progress, telling me some summary of each iteration. I actually do like the default, but unfortunately, I think PyOptSparse is intercepting it because normally you would see this kind of stuff each iteration. And that's what I want to see. This other stuff is probably more detail than I want, but that's, you know, not a bad thing necessarily. A little bit harder to parse. File print level, I can put more detail in the file. The default is 5. So again, yeah, that's actually what I like to see usually is this level of detail. I don't know why PyOptSparse isn't printing it. And there's a bunch of other stuff here that probably won't need, you know, you can print things with less frequency. There's a lot of options here that you're very unlikely to use. They're very deep into the details of the algorithm. Warm starting is a nice thing we won't use, but miscellaneous, so you could change the file name. The default was IPOPT.opt, IPOPT.out. It can be convenient to change that. So if you're running lots of optimizations, sometimes like in a loop, you want to get different names. You can go back later and look at them and see, oh yeah, that one didn't converge. And so that's a nice thing to have. Again, these are more algorithmic details. Algorithmic details that you won't change. There's something down here I was going to show you that you probably will change. I'm just trying to remember. Oh yeah, derivative checker, this is the one. So this is nice. There's a derivative test. Many optimizers have that built in. And it's a very good idea if you're providing derivatives to turn that on the first time. So let's do that. Since we just provided them. Let's see, what was it called? Derivative test. Derivative test. And then let's see, first order. I want, so the default is none. First order, check the first derivative. So it's going to do a fun inference internally and check it against the ones I provided to make sure they look good. And you can see there's more details like on the tolerance of that and whatever, but this should be good most of the time. So let's look at our output file. Let me make this bigger again. It says starting derivative checker for first derivatives, no errors detected. So if it saw any, it should tell me which ones, right? Like, so this one was off by this much, and maybe that's okay. Maybe I just need to adjust my tolerance, but usually that's an indication that something is not good. So I'm going to get rid of that one now because I don't want that to run every time. That's just going to slow it down. And I've checked them in this case. Yeah, I think that those are kind of the key options that you might use. Okay, so one other thing, well, I guess this is just a workaround because normally this stuff should be printed, and that's a big, huge advantage here is to monitor the progress as it goes as opposed to just after the fact. But we can do that from the file too if PyOptSparse is intercepting that. Just to show you that, let me artificially make this take way longer than it should. What is it, time? I'm just going to put in a sleep here just to make this really slow. Let's just make everything take each iteration or each function call it 2 seconds artificially here. So I'm going to run that. That's giving me tons of information, but I can look at my output file here, right? And notice that it's just going to update eventually. It's doing a lot of initialization. No, it's not updating. Interesting. I assumed that VS Code would do that. I can do it from the terminal. So it reloaded after the fact. So it's not reloading on the fly. There's probably an option for that. I don't know what it is, but I know how to do it from the terminal. So if I'm in the same directory, I could, for example, just use del, and it's now seeing my progress. And this is very helpful because then I can see if things are going crazy, right? I can look at my objective, make sure things are progressing, look at my constraint violations, and sometimes you'll see this start veering off, right? You don't want to wait till it decides to quit. You want to just cancel it and say, okay, something's going wrong, especially in the early stages while you're testing things out. This is very helpful. I'm sure the text editor could do this too, probably an option. You know, you may want to look at that if you're not comfortable with terminal, but that's another way to do it. So you can look at the file, but also of course reload the file periodically if you like to do that. But I would do something that is going to be continuously updating. If I figure out how to make it show here, I'll let you know. I mean, it is showing it here. It's just showing too much information that it's making it hard. So this is probably, oh, it's magically doing it now. Oh, this is exactly what I want to do. Okay, so it's showing my options and it's showing my history. That's perfect. So I can watch this as it goes. And that's great. I made it really slow. So maybe it was showing that all along and I just totally didn't notice because it was going by so fast and then it printed everything. So good. So it does do we want, put that print level in, and you can watch things as you go. So let's actually quickly look at what these are. I actually pointed out already the most important ones, but just so you can look at this, go back to the IPOPT documentation. Here it says output, and it explains each of these. Most of them are pretty detailed stuff that you won't care about, but this is the major iteration. This is the objective. This is the constraint violation. It's the infinity norm. So this is my maximum violation, the maximum absolute value of my violation. Most of these others you won't care about. Alpha, this primal one is kind of my step size. In that line search, and you'll notice if we go back here, most of the time it was 1, right? And that's typical, as we've discussed, that we're kind of taking our best, our first guess was good enough. Otherwise it's taking a different step. It had to backtrack and things. Last thing, which is perhaps not super clear in the PyOptSparse, I want to get some things out here. So I'd look here on solution. This says some things I can get out. So I want to get out X star. I don't want to print that. I want to print out X star, and notice it's capital S. That's important. It's a dictionary, so it's actually returning all of those X's. And I want, let's say in this case, areas. So let's print that out. Or let's say I want to store this to a variable. So actually, let me kill this. Well, I don't know. I got to get rid of my sleep here because I don't want to wait. Okay. Oh boy, I have to wait for this to finish running perhaps. I tried to kill it, but it's only just killing the display. Okay, there we go. We'll run it again. There we go, and there's my areas. Final objective, that's usually something I also want to. And this is not a dictionary, it's just the objective, so it's already pulled that out. There it is. I can assign that to a variable. It's actually an array because I could have multiple objectives. I can get the Lagrange multipliers, I can get a code. So IPOPT returns different codes. So if I don't want to go look at the file, I can look at these codes. 0 is solve succeeded. And then these other ones that this is good, solve to acceptable level. And then here's some ones. And you can look at the documentation if you're interested on what these might mean, but they're indications that things did not work well. All right, so I think that's it. And like I said, if we want to change the optimizer, simple as that. Later we could change it to, well, I have to get rid of these options because SLP doesn't have very many options. And yes, it worked well in this case. And later we'll use some of the gradient-free ones, so you can change those options as well. But probably the biggest benefit here, besides that it's usually, I would say, a better optimizer, is that I can see my optimization progressing here. I can watch, monitor the progression, kill the optimizer if I need to, right, to restart it, and I get a lot more available. There are a lot of other things in PyOptSparse. There are things about some advanced features where you can store your history, you can store everything along the way in a SQL database, and there's a visualizer to visualize things, a lot of other things, not really necessary for our purposes, but certainly you can take a look, and some of these may be useful to you in your projects if you're interested. Okay, that's it.